Listen to the war, and you will hear one engine everywhere. On the morning of June 6, 1944, off the coast of Normandy, thousands of small flat-bottomed landing craft claw through the gray channel, swell toward the beaches, each one driven by a single engine, and that engine makes a high, screaming, blower-whined roar that a soldier crouched in the boat never forgets. 10,000 miles away, on a coral island in the Pacific, a Marine Sherman tank grinds forward against a Japanese bunker, and the engine in its tail makes that same scream, doubled. On the Eastern Front, a Soviet tank column advances through the mud toward Berlin, and the engines driving it make that scream. Behind the lines, in a field hospital, the electricity that runs the operating room lights comes from a generator, and the generator makes a smaller version of that same scream. In a motor pool, a truck hauls ammunition forward, screaming. On a harbor tug, on a fishing boat pressed into naval service, in a searchlight unit, in a pump clearing a flooded dock, the same high mechanical wail rises and falls, scaled up and scaled down and arranged in a dozen configurations to fit a dozen jobs, but underneath, identical. The men who worked with it called it the Screaming Jimmy, Jimmy for General Motors, screaming for the sound that no one who heard it could forget. Its formal name was the General Motors Detroit Diesel Series 71, and it was, more than almost any other single piece of machinery, the engine that powered the American war effort at the level of the individual machine. It moved the boats that landed the troops, the tanks that fought the battles, the trucks that hauled the supplies, and the generators that lit the hospitals. And the reason one engine could do all of that, the reason a single design could power a landing craft and a tank and a generator and a truck, and the reason one engine could do all of that, the reason a single design could power a landing craft and a tank and a generator and a truck, this is the story of the engine that powered everything, and of the idea that led it. America went into the Second World War knowing it wanted diesel power, and understanding why it wanted diesel is the beginning of the story. Diesel engines offered a set of advantages that mattered enormously to a nation fighting a global industrial war. Diesel fuel is less flammable than gasoline, with a higher flash point, making a diesel-powered vehicle or boat less likely to erupt into flame when hit or when fuel spilled. Diesel engines, compressing their air far harder than a gasoline engine, extract more energy from every gallon, giving better fuel economy and longer range, which mattered on islands and steppes and oceans where every gallon had to be hauled forward at great cost. Diesel engines have no ignition system, no spark plugs, no distributor, no carburetor, an entire category of failure simply absent, and they tend to be durable and long-lived under hard, continuous use. For the punishing, around-the-clock demands of war, these were exactly the right qualities. But wanting diesel and having diesel were two different things, because through the 1920s and into the 1930s, the diesel engine had a problem. It was heavy and slow. The diesels of that era were massive, ponderous machines suited to ships and power stations and locomotives, where their great weight did not matter, but far too heavy and too slow-turning for a truck, a bus, a boat, or a tank. The world had powerful diesels and it had light gasoline engines, but it did not have a light, fast, powerful, compact diesel that could go into a vehicle. The engine America wanted for its war, a diesel light and quick enough to power the machines of mobile warfare, did not really exist at the start of the 1930s. It had to be invented, and the man who set out to invent it was not a diesel engineer at all, but the head of research for General Motors, a restless inventor obsessed with a problem the whole industry thought was impossible. Here is the paradox at the center of the story. The engine that powered such an astonishing variety of machines, boats and tanks and trucks and generators and everything in between was not a variety of engines. It was, in its essential design, a single engine, one cylinder repeated. The versatility that let it power everything did not come from designing many different engines for many different jobs. It came from the opposite approach, from designing one thing supremely well and then repeating it. The Series 71 was not a family of related designs. It was a single cylinder, one carefully perfected combustion unit that could be bolted together in different numbers and arrangements. to make engines of wildly different sizes and powers, all sharing the same fundamental parts. The resolution of the paradox is one of the great insights of industrial engineering, the building block principle. Instead of designing a small engine for a truck, a medium engine for a boat, and a large engine for a landing craft as three separate projects, General Motors designed one cylinder, one displacement, one set of internal components, and then built engines with 1, 2, 3, 4, or 6 of those identical cylinders in a row, and later in V arrangements of 6, 8, 12, 16, and even 24. A 2-cylinder version powered a small generator, a 6-cylinder version powered a truck or a boat. Bolt 2 6-cylinder versions together and you powered a tank. Every one of these engines, from the smallest to the largest, shared the same pistons, the same cylinder liners, the same injectors, the same fundamental architecture. This was why one engine could power everything. It was not one engine pretending to be many. It was many engines that were all underneath the same engine. That sameness was a deliberate and brilliant design decision that shaped the entire American war effort at the level of the machine. The popular history of wartime engineering loves the singular, heroic machine, the Merlin engine, the specific tank, the particular aircraft. It is drawn to the thing that did one job supremely well. It tends to miss the humbler and in some ways more profound achievement of the engine that did 1,000 jobs adequately, the ubiquitous workhorse that was everywhere precisely because it was not specialized. The Detroit Diesel Series 71 is exactly this kind of forgotten hero, an engine so common, so widely used, so much a part of the background hum of the entire war that it became almost invisible, noticed only as a sound, and the popular history misses the specific engineering idea that made it possible, the building block modularity that is genuinely one of the more important manufacturing concepts of the 20th century, and that the Series 71 embodied more completely than almost any engine before it. It misses how a single, well-designed cylinder, repeated, could conquer a dozen different applications. It misses the two-stroke diesel engineering that let the engine be so compact and powerful for its size, and it misses the sheer scale of the thing, the tens of thousands of these engines pouring out of a single Detroit factory to power the boats and tanks and trucks and generators of a global war. This is the story the singular machine histories overlook, the story not of one perfect engine for one job, but of one clever engine for every job, and of the design idea that let a single cylinder power a war. The engine began with Charles Kettering, the head of research for General Motors, and one of the most prolific inventors in American history. Kettering, born on an Ohio farm in 1876, had already given the world the electric automobile self-starter, leaded gasoline, and much else, and he ran the research laboratories of General Motors for nearly 3 decades. In the later part of his career, he became fixated on the diesel engine, convinced that the diesel's superior efficiency could be brought to everyday vehicles if only someone could make a diesel light and fast enough. The whole industry believed this was impractical. The diesel was, by its nature, a heavy, slow machine, and the conventional wisdom held it always would be. Kettering disagreed, and he had the resources of General Motors to prove it. The obsession had a famous trigger, a boat. Kettering bought diesel engines for his yacht to study them, and he became determined that General Motors should master diesel power. When Alfred Sloan, the president of General Motors, asked Kettering why the efficient diesel was not more widely used, Kettering explained the technical obstacles, and Sloan replied, in a decision that would echo for decades, that General Motors was now in the diesel engine business, that Kettering should figure out how the engine should run, and Sloan would provide the manufacturing. To get into the business, General Motors bought the Winton Engine Company of Cleveland in 1930, and Kettering set its engineers to work on the problem that everyone said could not be solved, a lightweight, high-speed compact diesel. The first great fruit of this program was the two-stroke diesel that powered the streamlined Burlington Zephyr train in 1934 and began the dieselization of the American railroad. But Kettering and his engineers wanted more than a locomotive engine. They wanted a compact diesel that could be built in quantity and adapted to everything, and to get it, they had to make a series of engineering choices that would define the engine for the next half-century. The first and most fundamental of those choices was to make the engine a two-stroke, and understanding why matters, because the two-stroke design is the source of both the engine's compact power and its unforgettable scream. A four-stroke engine, the kind in most cars, fires each cylinder once every 2 revolutions of the crankshaft, because the piston needs 4 separate strokes, intake, compression, power, and exhaust, to complete one cycle. A two-stroke engine fires each cylinder once every single revolution, on every downstroke, which means that for a given engine size and speed, a two-stroke can produce nearly twice as many power impulses, and therefore approach nearly twice the power as a four-stroke. For an engine that needed to be light and compact yet powerful, the two-stroke's power density was exactly the right choice. You could get the power of a much larger four-stroke from a smaller, lighter two-stroke. But the two-stroke diesel came with a fundamental problem that had to be solved, and solving it defined the engine's character. Because the two-stroke fires on every downstroke, it has no separate stroke to breathe in fresh air and no separate stroke to push out exhaust. It cannot inhale and exhale on its own the way a four-stroke can. It cannot, in engineering terms, naturally aspirate. The engine physically cannot run unless its air is forced in mechanically, and the solution to that problem was a device that became the signature of the whole engine family and the source of its scream, the Roots blower. The Roots blower was a mechanical air pump, a pair of meshing lobes spun by gears off the crankshaft, the same type of supercharger that hot rodders would later make famous, protruding through the hoods of drag cars. But on the Series 71, the blower was not there to add extra power in the way a hot rodder supercharger is. It was there because the two-stroke diesel simply could not run without it. The blower took in air and forced it, at a pressure slightly above atmospheric, through passages cast into the engine block and into a row of ports, openings machined into the walls of each cylinder. As the piston traveled down and uncovered these ports, the pressurized air rushed in through the side of the cylinder. This incoming air did 2 jobs at once, and this is the elegant part. It filled the cylinder with the fresh charge needed for the next combustion, and as it rushed in through the ports low in the cylinder, it swept the spent exhaust gases up and out ahead of it through poppet valves in the top of the cylinder head. Valves worked by the camshaft just as in a four-stroke, but used here only to let the exhaust escape. Fresh air in through the sides, exhaust out through the top, in a single continuous upward flow. Engineers call this uniflow scavenging, and it is a beautifully clean way to solve the two-strokes breathing problem. The blower spun faster as the engine sped up, and its rising mechanical whine, combined with the two-stroke firing on every revolution, and therefore producing twice the exhaust beats of a four-stroke, gave the engine a sound like nothing else, a high, urgent scream that seemed to belong to an engine turning twice as fast as it actually was. That was the screaming Jimmy, and the scream was the audible signature of the two-stroke, blower-scavenged design that made the engine so compact and so powerful for its size. There was a second key engineering choice that defined the engine and made it reliable enough to power everything, and it concerned how the fuel got into the cylinders. Most diesel engines of the era used a central injection pump that pressurized the fuel and then sent it out to each cylinder through a web of high-pressure steel fuel lines. Those lines were a chronic weakness, prone to cracking and leaking and failing under the relentless pulsing of the high pressure, and they were a common source of the breakdowns that plagued diesel engines. Kettering's engineers, drawing on ideas he had championed for years, eliminated them entirely. The Series 71 used what General Motors called the unit injector, one for each cylinder. The unit injector combined the high-pressure pump and the spray nozzle into a single compact device mounted right on top of each individual cylinder, worked by the same camshaft that operated the exhaust valves. The fuel was pressurized inside the injector body itself at the exact instant of injection, right at the cylinder where it was needed. Because the pressure was generated at the injector rather than pumped from a distance, there were no high-pressure fuel lines running around the engine at all, and the entire category of failures those lines represented simply vanished. This was a real reliability advantage, and reliability was exactly what an engine needed if it was going to power a landing craft in a combat assault, a tank in battle, a generator that a field hospital depended on. The unit injector, combined with the two-stroke blower scavenge design, gave the Series 71 its defining combination of compact power and dependable simplicity, and set the stage for the idea that would let it power everything. Now we come to the central idea, the concept that answers the question posed by the title, the idea that let one engine power everything. It was the building block principle, and it was genuinely revolutionary. When General Motors designed the Series 71, it did not design an engine in the usual sense. It designed a cylinder, one single, carefully optimized combustion unit with a bore of 4 1/4 inches and a stroke of 5 inches, displacing about 71 cubic inches, which is where the name came from, the 71 referring to the displacement of each individual cylinder. And then, having perfected that one cylinder, General Motors built engines by combining it in different numbers. An engine with a single cylinder, the 171, was a tiny power plant for the smallest jobs. 2 cylinders made the 271, 3 the 371, 4 the 471, and 6 the 671, each one simply that same identical cylinder repeated more times in a row. The 671, 6 cylinders in line, became the flagship, the workhorse, producing well over 100 horsepower, and it was the version that powered so many trucks and boats and doubled-up tanks. Later, after the war, the same cylinder was arranged in V configurations to make even larger engines, the 6V71, the 8V71, the 12V71, and the enormous 16V71 and 24V71, the largest of which used multiple cylinder heads borrowed directly from the smaller inline engines to keep the parts common. Every single one of these engines, from the one-cylinder 171 to the 24-cylinder 24V71, used the same pistons, the same cylinder liners, the same injectors, the same fundamental valve and blower and injection design. They were, in the most literal sense, the same engine in different quantities. The consequences of the building block design were profound, and they reached into every corner of how the engine was made, maintained, and used. Consider manufacturing first. Because every engine in the family used the same core components, General Motors could mass-produce those components, the pistons, the liners, the injectors, in enormous quantities on common tooling, achieving economies of scale that a range of unrelated engine designs could never approach. The factory did not have to tool up separately for a small engine and a medium engine and a large engine. It tooled up to make one cylinder's worth of parts, and made them by the millions, and assembled them into whatever size of engine was needed. This was mass production at its most efficient, and it let the engine be produced in the vast quantities the war demanded. Consider maintenance, which mattered just as much in the field. A mechanic who understood the 471 in a generator understood the 671 in a truck, and, in principle, the doubled 671 in a tank, because the fundamental parts and the fundamental design were identical. Training was simplified because learning one engine meant learning them all. Spare parts were simplified enormously because the same piston, the same injector, the same liner fit engines across the whole range of applications. A supply depot did not have to stock separate parts for a dozen different engines. It stocked the common components of the Series 71 and could keep running everything from a generator to a landing craft to a tank. In a war where logistics and maintenance in the field were as decisive as combat performance, this commonality was an enormous, often invisible advantage. The building block design meant that one engine's worth of manufacturing effort, one engine's worth of mechanic training, one engine's worth of spare parts could support an entire universe of different machines. That was how one engine powered everything, not by magic, but by the deliberate, brilliant decision to make everything underneath the same engine. Two further design features deepened the engine's adaptability and are worth understanding because they show how thoroughly the Series 71 was engineered to fit into anything. The first was its symmetry. The inline Series 71 engines were famously symmetrical, meaning that the major accessories, the blower, the exhaust manifold, the water manifold, the starter, and others, could be mounted on either side of the basic engine block, depending on what a particular application required. This flexibility mattered enormously when fitting the engine into the cramped and varied spaces of different vehicles and boats. If a boat's hull layout demanded the exhaust on the left, the engine could be built that way. If a truck's frame demanded it on the right, the same engine could be built the other way without redesigning the core. The engine adapted to the machine rather than forcing the machine to adapt to it. The second feature was reversibility. Many Series 71 engines could be built to run with the crankshaft turning in either direction, clockwise or counterclockwise, designated right-hand or left-hand rotation. This was especially valuable in marine applications where a boat with two propellers often wants them turning in opposite directions for balanced handling, which is easily achieved by installing one left-hand and one right-hand engine. A boat could be powered by a pair of Series 71 engines turning opposite ways, each the mirror of the other, but built from the same parts. Between the symmetry that let accessories go on either side and the reversibility that let the crankshaft turn either way, the Series 71 could be configured into a remarkable number of variants, all from the same fundamental design, to fit into and suit an enormous range of machines. The engine was not just a building block. It was a building block engineered from the start to be adaptable, to slot into whatever application needed it, in whatever orientation that application demanded. Now let us see where all of this adaptability actually went, application by application, because the breadth is genuinely staggering, and it begins with the boats that landed the troops. The single largest wartime use of the Series 71 was in landing craft, the flat-bottomed vessels that carried assault troops and vehicles from the ships offshore onto the invasion beaches. The numbers are extraordinary. Something on the order of 57,671 engines went into American landing craft during the war. About 19,000 of them powered the LCVP, the famous Higgins boat, the small wooden and steel landing craft that carried a platoon of soldiers and dropped them onto the beach over a bow ramp, the boat that a later general credited with winning the war. About 8,000 powered the larger LCM, the landing craft that could carry a vehicle, and about 9,000 were used in groups of 4 in a configuration called the Quad. In the larger LCI infantry landing craft, 4 671 engines driving 2 propeller shafts, producing 1,600 horsepower to move the bigger vessel. On D-Day, June 6th of 1944, when the thousands of landing craft ran for the Normandy beaches, an enormous proportion of them were driven by the marinized gray marine version of the 671. The scream of thousands of these two-stroke diesels was, quite literally, the sound of the invasion approaching the beach. The engine that Kettering had willed into existence to prove a point about diesel efficiency, the engine built around a single 71 cubic inch cylinder, was the engine that carried the assault waves onto the beaches of the greatest amphibious invasion in history. It landed the troops at Normandy, and it landed them across the islands of the Pacific, boat after boat after boat, each one screaming its two-stroke scream as it drove for the shore. No single engine put more Allied soldiers onto more hostile beaches than the Series 71. From the boats that landed the troops, follow the same engine into the tanks that fought the battles. When the Army needed a diesel engine for the Sherman tank, General Motors reached for the Series 71, but a single 671 was not powerful enough to move a 30-ton tank. So General Motors did what the building block philosophy invited. It used more cylinders, in this case by bolting two complete 671 engines together side by side and gearing their outputs into one, creating the twin diesel known as the GM 6046. Some 22,000 individual 671 engines went into Sherman tanks in these twin-engine packs, powering the M4A2 variant. And because the two engines were separately clutchable, a tank that took a hit to one engine could keep running on the other, a redundancy no single-engine tank could match. The Series 71 fought in more than just the Sherman. About 11,000 6-71 engines powered the M10 tank destroyer, built on the same diesel Sherman chassis, the tank hunter that carried a powerful gun to kill enemy armor. And about 4,000 went into Canadian-built Valentine tanks, most of which were sent to the Soviet Union under Lend-Lease. All told, some 39,000 Series 71 engines went into armored vehicles during the war. The diesel Shermans went overwhelmingly to the Soviet Union, where the Red Army, which ran on diesel and prized the engine's resistance to fire, drove them all the way to Berlin and called the tank the Emscha, and to the United States Marine Corps, whose landing craft already burned the same diesel, giving a fuel commonality that simplified everything on a Pacific beachhead. The same engine that landed the Marines, in other words, also powered the tanks they fought in once ashore. One-cylinder design, one-engine family, carried the troops to the beach, and then fought the battle they had come to fight. Beyond the boats and the tanks, the Series 71 spread into a vast web of less glamorous but utterly essential wartime jobs, and this is where the phrase "powered everything" becomes literal rather than rhetorical. The engine hauled freight and troops as the power plant of trucks. It had originated before the war, powering the buses of the American highway, the intercity coaches whose smooth diesel power the Series 71 had first been built to provide, and that same bus and truck heritage carried into wartime transport. But it was in auxiliary power that the engine's building block versatility truly showed its breadth. The smaller members of the family, the 271, 371, and 471, were ideal for driving generators, and generators were everywhere in the war, providing electricity for field hospitals, command posts, radar stations, searchlight batteries, repair depots, airfields, and countless other installations that needed power where no power grid existed. A 471, its block strengthened to endure battlefield conditions, would sit in a generator set and produce the electricity that lit an operating room or powered a radar. The same engine family drove pumps that cleared flooded docks and dewatered ships, compressors that ran pneumatic tools, welders that repaired damaged equipment, and the auxiliary machinery of countless vessels and installations. On a ship, a Series 71 might drive the main propulsion of a small craft, while another, smaller Series 71 served as the auxiliary generator, both built from the same cylinder. The engine-powered fishing boats pressed into naval service, harbor tugs, and workboats of every description. Wherever the war needed mechanical power or electrical power in a compact, reliable, field-maintainable package, the Series 71 was there, in one of its many configurations, screaming its familiar scream. It hauled the supplies, it lit the hospitals, it pumped the water, it ran the tools, it charged the batteries. The engine did not just power the dramatic machines of war, it powered the vast, unglamorous infrastructure that kept the whole war machine running, and it did so with the same building block design that powered everything else. Step back and consider the sheer scale of Series 71 production during the war. because the numbers convey what an industrial achievement it was. Detroit Diesel, the General Motors division that built the engine, ramped its production to extraordinary levels. From around 9,000 engines in 1941, output climbed to nearly 58,000 Series 71 engines in 1943 alone, and to over 60,000 in 1944, with well over 100,000 GM diesels built across the course of the war. The 100,000th 671 was ceremonially delivered to the Navy in 1944. This was mass production of a complex diesel engine at a scale never before attempted, made possible in significant part by the building block design, which let the factory concentrate on producing the common core components in enormous volume. Behind those numbers was a factory and a workforce operating at full stretch, some 4,300 workers producing tens of thousands of engines a year, feeding the insatiable demand of a global war for boats and tanks and trucks and generators. And the demand was insatiable precisely because the engine was so versatile. A more specialized engine would have found a smaller market, but the Series 71, able to power almost anything, was wanted for almost everything, and the factory ran flat out to supply it. Material shortages forced substitutions, aluminum for steel in non-structural areas to preserve steel for other uses, but the engines kept flowing. The scale of Series 71 production was itself a weapon, a river of compact, reliable diesel power flowing out of Detroit to drive the machines of the war, tens of thousands upon tens of thousands of engines, all built around the same single perfected cylinder. It is worth pausing to note how differently the diesel question played out in Germany, because the contrast illuminates the specific nature of the American achievement. Germany, the nation of Rudolf Diesel, who had invented the diesel engine, possessed superb diesel engineering, and it used diesel power extensively, above all in its submarines, where reliable, efficient diesel engines were essential. Germany built excellent diesel engines, but Germany did not have, and did not build, anything quite like the Series 71, a single, mass-produced, building block diesel that powered a vast range of applications from one common design. Part of this was the German engineering culture, which tended toward the specialized, purpose-built solution, the engine designed precisely for its task, rather than the flexible, standardized building block designed to be adapted to everything. German engineering excelled at the bespoke and the optimized, and was less drawn to the American approach of a common design, mass-produced and adapted. And part of it was resources. Germany was chronically short of diesel fuel throughout the war, dependent on limited synthetic production, and had to husband its diesel for the submarines and vehicles that most needed it, which limited how freely it could deploy diesel power across every application the way America could. America, with its abundant petroleum, could pour diesel into landing craft and tanks and generators and trucks without the constant fear of running short. The Series 71 was, in this sense, a characteristically American answer to the diesel question. The standardized building block mass-produced in overwhelming quantity and adapted to everything, fueled by a resource abundance that Germany could not match. Germany built fine diesels for specific jobs. America built one diesel for every job and built it by the 100,000. The war ended, but the Series 71 did not. If anything, its wartime service was only the beginning of one of the longest and most remarkable production runs in the history of the internal combustion engine. The engine that had powered the landing craft and the tanks and the generators of the war went home and powered the peace. It returned to the buses and trucks it had come from, and it spread into an ever wider range of civilian applications, powering fishing boats and tugboats and yachts, fire trucks and construction equipment and farm machinery, generators and pumps and compressors, in a career that stretched on for decades. The building block design that had made it so versatile in war made it just as versatile in peace, And the same cylinder that had screamed toward the Normandy beaches went on screaming across the post-war world. The Series 71 remained in continuous production from 1938 all the way to the summer of 1995, a span of 57 years, finally retired not because it had become obsolete in function, but because tightening emissions regulations at last favored cleaner four-stroke designs. After the war, the V configurations were added, extending the family further, and the engine's descendants and copies spread worldwide, including in the Soviet Union, which reverse-engineered the engine from Lend-Lease examples and built its own versions at the Yaroslavl factory to power Soviet trucks for decades. Detroit Diesel built more than 5 million engines over the years, more than 1 million of which are reportedly still running somewhere in the world today. The Screaming Jimmy became one of the most familiar mechanical sounds of the 20th century, on the highways, on the water, on the job sites, its distinctive two-stroke wail instantly recognizable to generations of mechanics and operators. The engine that powered everything in the war went on powering everything for half a century after it. The lesson of the Series 71 is a lesson about a particular kind of engineering wisdom, the wisdom of designing not the perfect solution to one problem, but the adaptable solution to many. General Motors could have designed a specialized engine for each wartime application, an optimized truck engine, a separate optimized boat engine, a separate optimized generator engine, each one perhaps slightly better at its specific job than a shared design would be. Instead, it designed one cylinder supremely well and built everything from it, accepting that a building block engine might be very slightly less optimal for any single application in exchange for the enormous advantages of commonality in manufacturing, in maintenance, in training, in spare parts, in sheer producible quantity. And in the context of a global industrial war, those advantages of commonality vastly outweighed the small cost in specialization. This is a lesson that runs through the whole American approach to the war, the preference for the standardized, the producible, the maintainable, the adaptable, over the perfectly optimized but specialized. The Series 71 embodied it at the level of the engine. One cylinder, repeated, adapted, mass-produced, powering everything from a generator to a landing craft to a tank, maintainable by a mechanic who understood the one design, supplied by a depot that stocked the one set of parts produced by a factory tooled for the one core component. It was not the best possible engine for any single one of its jobs. It was a very good engine for all of them, and its universality, its adaptability, its producibility made it worth more to the war effort than a dozen specialized engines would have been. The building block beat the bespoke, not because it was better at any one thing, but because it was good enough at everything and could be everywhere. And being everywhere in a war fought across every ocean and continent was worth more than being perfect anywhere. In a war decided by what could be built and maintained and put everywhere at once, what was everywhere was a single cylinder, repeated. The Detroit Diesel Series 71 was not a family of engines so much as a family built from one engine, one carefully perfected 71 cubic inch cylinder, bolted together in ones and twos and threes and fours and sixes, arranged and rearranged, mounted left-handed or right-handed, its accessories hung on either side to fit into and power almost every machine the war required. It landed the troops at Normandy in the screaming Higgins boats. It fought the battles in the diesel Shermans that drove to Berlin and stormed the Pacific Islands. It hunted tanks in the M10. It hauled the supplies in the trucks. It lit the field hospitals through the generators. It pumped the water and ran the tools and charged the batteries of a global war. And underneath, in every one of those wildly different machines, it was the same engine. It could do this because Charles Kettering had willed a compact, high-speed diesel into existence when the whole industry said it was impossible, and because General Motors had made the brilliant decision to design not an engine, but a cylinder, a building block that could be combined into whatever size and shape a job demanded, all sharing the same parts, the same maintenance, the same mechanics, the same mass-produced components flowing out of a single Detroit factory by the tens of thousands. The two-stroke design gave it compact power. The blower gave it breath and gave it its scream. The unit injector gave it reliability, and the building block principle gave it the universality that let one engine power everything. In a war fought between industrial systems, the system that could design a single cylinder and, from it, build the engines for its boats and its tanks and its trucks and its generators, and produce them by the 100,000, and maintain them all with one set of parts and one body of knowledge, was a system whose depth and flexibility its enemies could not match. Germany built superb diesels for specific jobs and never had enough fuel to use them freely. America built one diesel for every job and poured it across every front of the war. The Series 71 was never the perfect engine for anything, and it was a very good engine for everything, and it went on being a very good engine for everything for 57 years. It screamed toward the beaches, it screamed across the islands, it screamed on the highways and the harbors and the job sites of the world it helped to save. One cylinder, repeated, powered a war and then powered the peace. That was the idea, and the idea was enough. In a war decided by what could be everywhere, the thing that was everywhere was a single screaming two-stroke cylinder, and it was more than enough.